Okay, what we've got here is a Faulhaber or micromo, a US or a CAN-based motor controller board here. This is a brush motor, cordless brush motor, gearbox here, and encoder. That's a DC servo motor controlled by this controller board. It uses a CAN bus interface here. This is the CAN bus terminating resistor, and this over here is a linear DC power supply that we're going to eventually use, 3.5 amp 24 volt DC supply, which will eventually power all of the DC powered circuitry for the telescope. This here is a PCAN digital to CAN interface to pick up the guider paddle inputs, the mechanical switches for the hand paddle, plus the ST4 guide port signals. And this talks on CAN also. So there'll be declination and RA drive motors and controller boards talking on CAN, and the paddle interface and the ST4 guide port here. So we're going to go ahead and start the motor at a slow speed, which is close to the tracking speed, and then we'll go to a fast speed and then slow it down and reverse it, all the normal things that you'd expect a motor to do. Okay, so this is our scope drive program. This is a Visual Basic program which runs the mount. You can see here it's got the typical slew speed control. It's got the north, south, east, west buttons to control the motor, to give you direction control. You can see the encoder tick position. Right now I'm driving the declination axis motor. You can see those tick positions increasing. It also has a current monitor, and then over there you'll see the position, RA and declination. So I can speed the motor up and you'll see current goes up. You'll see the position changing more rapidly. There's the resulting equivalent scope position. Right now I have right ascension slewed to declination just for debugging purposes. And stopping the mount, go the other direction. You can see the CAN message count going back and forth, because this whole thing communicates on CAN. It's running sort of quasi real time. There's a date, Julian date, current date, and then that makes the equivalent sidereal time based on the longitude, which is fixed for this case. This program works in, as I said, it runs on Visual Basic. It runs in basically a 10 millisecond frame, quasi real time in Windows, and it can do that because this PCAN controller, the CAN API, which is provided by Grid Connect, it's an American representative of a German company called PCAN. That API lets me send packets back and forth to the CAN controller device, so those can be queued up for transmission. And CAN messages they have a 11-bit identifier, and then there's a 8-byte data packet. And there's a standard industrial protocol called OpenCAN or CAN-Open, and this uses part of that. It uses also a proprietary mode that Faulhaber, which is the controller company, makes. We're going to use CAN to both to run the encoders and to run the mount control, drive motor control, to read the ST4 inputs, to read button presses for slewing for the hand paddle. The ST4 port is the guide port. We also are going to use a tilt sensor, which is a little bit unique. There's a CAN bus based tilt sensor that'll sit on the mount, and we'll zero the mount position out in absolute position by going to 0 degrees on the tilt sensor in east-west and north-south, and that gives us a zenith position that tells us we're at a known rate ascension and declination, and then from that we will go off to our first reference star and then do a second sync on that reference star. And that's going to be kind of our basic mount rough positioning model. And then the tilt sensor also gives us some limiting control, and it kind of does the function of homing switches. So the tilt sensor is sort of a new kind of unique thing. Another unique thing about this mount is that it has no clutches for balancing. It uses current monitoring, and that's a nice feature of those Faulhaber controllers, is that they do have a lot of parameters like velocity, current, position, are all transmitted back in real time on CAN bus, and so we get those at a high rate, and then we can use that to check for balance, by going to a test position, driving the motor in each direction, and then comparing currents, and then from that we can do an adjustment to kind of give us the balance that we want. It's right now, that's about 800 lines of Visual Basic. That's all custom coded. It also has a serial port interface that goes out and talks to it uses the Nexstar protocol, so it can talk to any charting program to display the current scope position, and at some time in the future it'll be able to receive data too over serial, and so then it'll be able to accept positioning commands, and that'll allow the scope to be driven from any of the standard mount control software packages. And because it's Windows, this could also have an ASCOM driver written for it, although I'm not sure that's going to happen. So it's coming along. That's sort of where we're at now. Haven't got the tilt sensor integrated, but sort of the main thing now is to finish the mechanicals and debug some more of the code and get the final little bits working.